Hello everyone and welcome to this video about arbitrary precision arithmetic. We're going to be covering in this first episode the basics of arbitrary precision arithmetic, how it works, why it's used, a basic example of an implementation of arbitrary precision arithmetic. So let's jump right into it. What is arbitrary precision arithmetic? It's a system of storing and calculating with numbers where the precision of a number is limited only by the memory of the computer. And some examples of programming languages that have built-in support for arbitrary precision arithmetic include Haskell, Python, and Ruby, and I'm sure there are many others. Arbitrary precision arithmetic contrasts with fixed precision arithmetic, where numbers are limited only to a certain amount of bits. For example, in C, where there are many different data types for numbers, representing different fixed precisions of integers and floating point numbers. And in this series, we'll essentially just be covering arbitrary precision arithmetic for integers. So why is arbitrary precision arithmetic used? Essentially, it's only used whenever speed is less important than precision. If you're calculating the trillionth digit of pi, it doesn't matter if the program runs substantially faster if the precision is just off, even by a tiny bit. And another usage of arbitrary precision arithmetic is cryptography, where numbers of hundreds of digits are utilized. So how does arbitrary precision arithmetic work? To understand how it works, you first have to understand how numbers are stored in fixed precision arithmetic. In fixed precision arithmetic, each bit of a number, or I guess a digit, represents a different value depending on its position. Since we're using bits, the value of each digit will be based on a power of 2, so 2 is called the base, or a radix. For example, with this number, working backwards from the least significant bit, each bit is worth 1, 4, 8, 32, and 64, because those are the powers of 2 for each of their respective positions. And that gives you a total of 109, meaning that this string of bits represents 109. In fixed precision arithmetic, there's a fixed size for the amount of bits that you can store in an integer. So with the example I just gave, it's an 8-bit number. So if we're using an 8-bit integer, the maximum number that could represent is 255. And once you get to that, once you try to add 1, there's just no more space. In arbitrary precision arithmetic, not only is the amount of digits not fixed, but usually the base of the digits is set to a number larger than 2. So theoretically this could be any number, like in our decimal system, the base is 10. However, programming languages are designed to be efficient, so usually the base of an arbitrary precision integer will be set to some high power of 2 that's close to the maximum size of the fixed precision integer that they're working on. For example, in Python, the base for arbitrary precision integers is often 2 to the power of 30, which is close to C's maximum value for the int. In fact, it's half of it. We'll now go through the start of an implementation of arbitrary precision integers that I've written in Python. So, as we can see in this example code, I've created a class, biguint, because it's an arbitrary precision unsigned integer. And you can implement a signed integer if you want, but for these purposes I'll just be sticking with the basic unsigned integer algorithms. It's not too difficult to implement signed algorithms from that. Anyway, as you can see, I've set the base of this class, of this integer, to 2 to the power of 30. And when the integer is initialized, you can put in a list of digits to initialize it to, And those digits, of course, are all in base 2 to the power of 30. So there's an important thing to note, however. In this system, the least significant digit comes first, and the most significant digit comes last. So it starts with powers of 1, and then it goes up to powers of 2 to the power of 30, and the next digit's 2 to the power of 60, etc. Instead of, as you might normally expect with normally written numbers, where the most significant digit, the highest value digit, comes first. So what this does is when you initialize it to a list of digits, it iterates through each of those digits and then just checks if any of the digits are larger than the base, and if it is, then it just gives a value error. Of course, you can't have a digit that's larger than the base. Then the next method that I've implemented is just converting it to a regular Python integer, an int. And it starts with a total of 0, because if you have no digits, it's just 0, it's nothing. And then it iterates through all the digits that you do have, and multiplies each digit by the base to the power of the position of the digit. So, as I stated before, the 0th digit, the first digit, will be 2 to the power of 30 to the power of 0 times that digit, which is just that digit times 1. And then for the next digit, digit number 1, it will be the digit times 2 to the power of 30 to the power of 1. So 2 to the power of 30, and then as you go up, 2 to the power of 60, 90, etc. So it adds that number to the total, and it returns it as a regular Python integer. So then the next function is very simple, just converting it to a string, calling this integer method, and then converting that to a string itself. And now I have 3 examples of my big uint class in usage. The first number x is just an empty list of digits, it's just 0. So when you print that, it should print 0. The next one is y, which is just 57. And since that's the first digit, the 0th digit, it's the base to the power of 0 times 57, so it's just 57. And the next one is a list of 10,001. This means that the total will be 10,000 times the base to the power of 0 plus 1 times the base to the power of 1. And I haven't calculated that, so... Oh, whoops, I almost forgot to print the other numbers. There we go, print y and print z. Anyway, if we head into command prompt... Okay, so let's now run the file. So as you can see, each of the digits were as expected, they were printed, and that brings us to the end of this episode. In the next episode, we'll go over some basic arithmetic algorithms, in particular addition and subtraction. So subscribe if you want to see that, and have a good day.